Log on, tune in, find out. Another good idea from Cambridge.
Scattering from isospectral graphs.
My zoologist friend showed me this photo of the just born sparrows, and she told me that she could not distinguish between them by their looks, but she wonders how will they sound when they will open their beaks. Can one hear the shape of a drum? This famous question was asked by Mark Katz in the 60s. And the question means whether it is possible to reconstruct the shape of a drum from its spectrum. Or another version of the problem is it possible to have two different drums which have the same spectrum? And we will call them isospectral drums. Let's formulate the question a bit. So a drum for us would be an elastic membrane which is attached to a solid frame, and then we solve the wave equation for the drum and actually seek the eigenvalues of the Laplacian. These are the spectrum of the drum, and the boundary conditions are the Dirichlet boundary condition. The function vanishes on the boundary. Here you can see a few examples of wave functions on the Sinai drum or Sinai billiard. So this was a short formulation, and now quickly let's answer Katz's question. So the answer was given something like 30 years later by Gordon and Webb, whom you can see here. These two mathematicians, who are also a couple in life, formed these two drums, which are isospectral. You can see these drums also on their T-shirts, and they also hold paper models of drums which look different than these kind of drums, but actually are the same example, and we will understand why. So no, one cannot hear the shape of a drum. Now, how can we prove isospectrality? The most basic proof of it is due to the concept of transplantation. A transplantation is actually a transformation which takes an eigenfunction on the first drum and transforms it to an eigenfunction on the second drum with the same eigenvalue. And this transformation is also invertible, meaning that these two drums have the same eigenvalues. They are isospectral. So pointing on such a transformation, which is called transplantation, proves isospectrality. Let's see how it is done. We plot here these two drums. We can see that each of the drums consists of 7 basic building blocks, which are triangles. We denote the triangles by letters in this drum. And then the transformation is as following. Each triangle on this drum gets a linear combination of values of 3 triangles from the first drum. So for example, this triangle has the values a minus b minus g. So this triangle minus this triangle when it is being put on top of triangle A minus g. All the values are values of functions, of eigenfunctions. So obviously, if here we had an eigenfunction, we take linear combinations, and this is also eigenfunction inside each triangle because our equation is linear. So we only need to check that the new eigenfunction indeed obeys boundary conditions, is 0 on the boundary, and also in between triangles that it is continuous and its derivative is also continuous. So let's briefly check it. For example, watch the dashed line here. So the dashed line here actually equals the dashed line here of A, which is 0, minus the dashed line of B, which is also 0, minus the dashed line of G, which is also 0. So this dashed line equals 0. Now, how about the dotted line? The dotted line here is the dotted line of A minus the dotted line of B, which are the same. So they cancel each other and vanish, minus the dotted line of G, which is 0. So the boundary condition also obeyed here on the dotted line. And one can continue and check it on all the boundary. And now let's see the continuity argument. So let's check, for example, the element minus b and minus c. The element minus b and minus c, you can see here that this is the solid line, and the solid line indeed separates here between the triangles b and c, so they are taken together to put on these two triangles with a minus sign, and therefore the value is continuous only due to this minus b and minus c. Minus g and minus e, you can see that it is similar because also the solid line separates them. And then you have a and minus a, so a has a 0 value on the solid line. You take a and minus a and you just get an antisymmetric function which is also continuous. So there is a continuity of the value and of the derivative, and if we check it on all the drum, we get the full transplantation. And now let's go on. Actually, this argument is so basic that Chapman in 2000 offered to prove transplantation using an origami proof. So how one can do it? You take 3 paper copies of this first drum, you fold them, you fold each of them, and then you get 3 folded copies. Now, when you fold them, you consider either the value or minus the value, depending on the direction of the folding, and then you get continuity for free without all this discussion that we had on the last slide. So you just take these 3 copies, which are continuously nice, you put them one on top of the other, and you can see that they fit into the frame of the second drum. So you can prove also isospectrality by origami. Let's go on. Actually, all this concept is due to symmetry. The only thing that matters is our symmetry, which means how do we put our triangles together. So we put our triangles together in a certain way, in a certain recipe, here in this drum, and in the other drum in a different way. Now, once we do this, we don't really need to use a triangle. We can take a different triangle, or soon even a different shape, and if we reflect the triangle in exactly the same way, we get again 2 drums which are isospectral. So the only thing here is due to symmetry, and then we can consider many other options, like replacing the triangle with a square, but reflecting the square only along 3 of its edges, not using the 4th edge. And then we get that this drum is isospectral to this drum. We can continue playing with this, and now you can see the paper models that Gordon and Webb were holding. We just take the triangle and cut it, so we get these isospectral drums. We can also cut it in a nasty way, and then we ruin the connectivity. So we get 2 drums which are isospectral, but each of the drums consists of 3 connected components. So this drum is isospectral to this drum. Okay, this is about some symmetry gains. Now, we wish to ask ourselves furthermore. So we see that we have isospectrality now, but what happens if we listen to these drums from the outside? So this question was checked by the mathematicians Okada, Shudo, Tasaki, and Harayama. They did a numeric work, which is the following. They took these 2 drums and checked the poles of their scattering matrices. The poles of these drums' scattering matrix are indicated by circles. This is the complex plane. And k is the parameter, which is square root of the eigenvalue. And the poles of these drums are indicated by triangles. And you can see that the poles are different. So their conjecture was that isospectral drums, or maybe isospectral objects in general, can be distinguished if one checks the poles of the scattering matrices. And in this talk, we want to examine their conjecture and shed a new light on it. How we will do it? Because this is a workshop on graphs, we will use graphs in order to learn some things about drums. So in the beginning, we will talk about scattering matrices for quantum graphs, quite briefly. Then we will present an isospectral construction, which allows to build isospectral graphs and more. And then we will combine and check what happens when we scatter, but from isospectral graphs. And we go back to drums and see what we have learned. So let's start. Quantum graphs, very briefly. This is a graph, vertices and edges. The graph becomes metric when we put a length to each edge. And our way to describe vertex conditions on the graph is by using unitary scattering matrices that are put on the vertices. These unitary scattering matrices are of dimension which fit the degree of the vertex. So for example, sigma 1, sigma 2, sigma 6, and sigma 5 are of dimension 1, and sigma 3 and sigma 4 are 3 by 3 unitary matrices which describe the vertex conditions. Now we seek for eigenfunctions of the Laplacian with eigenvalue k squared. These eigenfunctions can be described on the edges as a linear combination of e to the minus ikx and e to the ikx with coefficients a and another a in and a out. So therefore, 10 coefficients are sufficient to describe an eigenfunction on this graph because this graph has 5 edges. Now here, this representation obviously has second derivative k squared, minus k squared actually, but we also need to satisfy vertex conditions. Satisfying vertex conditions is due to the following condition. We need our vector A of 10 coefficients to be an eigenvector of uk with eigenvalue 1, where uk is this giant matrix, which is a product of two 10 by 10 matrices. The matrices are as following. We have one matrix which describes the scattering from the vertices. So you can see here that each scattering matrix of the vertices is being put as a submatrix of this big scattering matrix. This is, by the way, still not the scattering matrix that we want to discuss. We're approaching it. So we have here sigma 1, sigma 2 until sigma 6, and sigma 3, for example, has 9 elements here in this big red matrix. And the blue matrix describes the phases. So it is of the form e to the ikl, where L are the length of the edges. I'm not sure that it is visible in a good way, so here it is a bit bigger. This is the blue matrix times the red matrix. And this product forms u of k, and we seek of eigenvectors of u of k with eigenvalue 1, and then we have our solution, our eigenfunction. So the k's for which we have a solution for this equation are exactly the spectrum of the graph. This is how we find the spectrum. The a's describe the coefficients which give us the eigenfunction, and here you can see 3 eigenfunctions, typical eigenfunctions of this graph drawn here. Now let's do the scattering problem from the outside. In order to get to the outside, we need to connect infinite leads to some vertices of the graph. So in this example, we connect 2 leads to these vertices, and then we can describe the function on the leads also as a linear combination of e to the minus ikx and e to the ikx. And the new coefficients are c1 in, c1 out, c2 in, and c2 out. Now we do the same trick with the matrix u of k. This time the matrix grows bigger. It is not 10 by 10, but it is 12 by 12 now, because we have added 2 new coefficients for C1 and C2. So this is the new matrix. The whole matrix, by the way, this red matrix is unitary as a whole because it consists of unitary submatrices. And for a real value of k, these are just phases, so the whole u of k is unitary. Let's put it in a bit more normal human form. So this is what we have. We seek for solution of this kind of equation. A's are the coefficients within the graph. C in, and C out are the coefficients on the leads. And this is our matrix u of k. We divide it to parts. So the equation is actually like this. We write it explicitly, and by doing some algebraic manipulation, we can express C out in terms of C in. Expressing C out in terms of C in gives us what is called the scattering matrix. We send waves inside using the coefficient C in, and we see how the waves are reflected to the outside using the coefficient C out. So this is the scattering matrix. Now from it one can study the poles. Obviously the poles of this matrix are due to zeros of 1 minus u tilde. Now I remind you that this whole matrix was unitary, so u tilde was unitary, for a real value of k it was unitary. So u tilde for a real value of k is subunitary. Therefore for real values of k we do not have zeros of 1 minus u tilde. In order to have zeros we need k to have some negative imaginary part which would make u tilde, which would enable u tilde to have eigenvalue 1, and then we will have our poles. So all our poles are below the real axis, just as in the case of drums. This is what we have on graphs. And again, we recall the original problem of drums, and we see that there is indeed analogy, at least in the positions of the poles. So this is the scattering matrix part. Now, but we want to discuss scattering not just from any graph, but compare isospectral graphs. In order to do this, we need to discuss isospectral construction, how isospectral graphs arise. So let's present a theorem which enables isospectral construction. The theorem goes like this. We start from gamma, which is a certain graph. Here is an example for a graph gamma, which obeys some symmetry group G. This graph, for example, is a square, and it obeys the symmetry of the square, the dihedral symmetry. Now we take some subgroup of the group and some representation, and there is some algebra behind it, which I will not dwell into. But the bottom line is that using the symmetry and the big graph, we can construct quotient graphs, which are, in this case, this graph and this graph. And the quotient graph are isospectral. Now, specifically in this case, you can see that the quotient graphs are actually subgraphs of the big graph gamma. Each of them forms a quarter of the big graph, and they have also vertex condition. So they have Dirichlet vertex condition on these vertices and Neumann on this, and similarly here. Now, how exactly these quotient graphs are derived and how the vertex conditions are derived will not be done here, but the important thing is that everything is due to symmetry. And even more important is that we have the next theorem that says that using this construction, the graphs that we obey also have the transplantation property, which you may recall from my previous slides. So they obey a transplantation, which we will soon use. And just one remark is that this construction also can be applied for drums and manifolds. So we will later indeed would be able to ask ourselves why the drums have different behavior. And very important is that this theorem is actually has a version due to Sunada, which sits in the audience, and this version of the theorem you probably know. Sunada's theorem is actually was the key that enabled the first example that you've seen in my slide of Gordon and Webb. So this is related to the theorem, to Sunada's theorem. Now let's go on for transplantation. On this example, the transplantation goes as following. We have here two building blocks actually. This is one building block. You see a straight line and a semicircle, and another building block, and you can see that this graph consists also of the same building blocks. So the transplantation here in this example is very simple. It is actually a linear combination. Here we take A minus B, when this is A and this is B, and here we take A plus B. And the notations are similar to the examples of drums that you had before. Therefore, the transplantation matrix is very simple, 1 minus 1 and 1, 1. Now, since all this isospectral construction is due to symmetries, we can also connect leads to the original graph in a way that will not ruin the symmetry, the original symmetry of the square. So either in this form or in this form, and then we use the construction. You do not need to understand the construction in order to understand that these are the quotients. You just apply the same trick of taking a quarter, and it works. And this means that these couple also obey transplantation property, and this couple also obey transplantation property. And now the scattering matrix, how we connect it. So let's take these two graphs, put them upstairs. Now we said that there is transplantation between this graph and this graph. How does it work? So this is now almost the bottom line regarding the scattering matrix. So we have that the function on the leads on this graph, g on the leads, is t multiplied by the values on the leads of this graph. Specifically, the values on the leads can be described as coefficients. Here I use vector g instead of the vector c that you had before. And here I use the vector f for the second graph. So we have this relation for the transplantation. But since the ingoing exponent and the outgoing exponent cannot mix, then we have that actually the f in is connected to the g in by the transplantation. The ingoing coefficients of one function multiplied by the transplantation matrix give the ingoing coefficients of the second function, and the same for the outgoing. Now we recall that the ingoing and the outgoing are related by scattering matrices, S1 for the first graph and S2 for the second graph. Now that we have all these equations, we can algebraically manipulate it and notice that f out is just this matrix times f in. It means that the scattering matrix of f, or S1, is just t minus 1 S2 t. So very simple relation. Actually, scattering matrices of isospectral graphs are conjugate to each other. Then obviously they have the same poles. Okay, so now the question remains, what happens to drums? Let us summarize what we have so far. We define graphs gamma 1 and gamma 2 to be called isoscattering if there is some version of turning them into scattering systems such that they have the same poles. And we have actually seen that using isospectral construction, we can construct isoscattering graphs. So we can construct isoscattering graphs from plane. Another option is to take graphs which are known to be isospectral, like these two, and understand how one should connect leads to these graphs in order to show that they are isoscattering. And there is more than one way. There are various ways of turning isoscattering graphs, isospectral graphs into isoscattering. And the only method that we need to use is to understand the bigger symmetry that was used in order to construct this isospectral pair. So we've seen that we can add leads in this format or in this format or in many other formats that are not shown here. Now, again, I emphasize the isospectral construction is only due to symmetry. So it can be used not just for graphs, but also for drums and for manifolds. So what fails in this example of these drums? And we are close to understand it. In order to understand it, let us turn these drums into graphs. We can do it in the following way. These drums, we've seen that they consist of 7 building blocks, 7 triangles. We can replace each of the triangles with a star graph of lengths A, B, and C. And then follow again the same recipe of reflections and get this big graph. Therefore, from these two drums, by the simple replacement of the triangle by a star graph, we get two graphs which are isospectral. Just as you've seen in the previous slide, instead of taking a cutted triangle, we just take a graph. So these two graphs are not the same, but they are isospectral. And their isospectrality is, again, can be derived from Sunada's theorem or from a theorem that I've shown you before. Therefore, there is a transplantation that turns the values of eigenfunction on this graph to the value of the eigenfunction on this graph. Therefore, we can also connect leads in appropriate positions on these graphs, and we will get that these graphs are isoscattering. So another evidence that there is isoscattering, though these graphs originate from the drums. So what is missing is the bottom line of the talk is that we need to go to the origin of the isospectral construction and ask ourselves how the drums were constructed. And the drums were constructed from the Poincaré disk, hyperbolic plane, or at least this is a certain version of construction using Sunada's theorem or the other theorem that I've shown. So we take the Poincaré disk, we have a certain tessellation of the disk to triangles, and then by certain group that I do not show here, we can divide and take a certain subdomain of triangles. So we take a certain subdomain here, we take another subdomain here. Now again, the key point is that the thing that matters is which triangles do we take and how to reflect one triangle in order to get the others. Then this work was done by Busser, Conway, Doyle, and Semler. Then they understood that actually they can take this hyperbolic triangle and turn it into a triangle on the plane and reflect the triangle exactly in the same way as was done here. And then they get a planar drum. They wanted the planar drum because this was the question of cuts. This was the original question that they wanted to answer. Of course, they were not the first ones. They did it, as you can see, after Gordon and Webb. But they explained the example in these terms. So you do it like this, and then you take this triangle, and again, you reflect it in a different way, and you get these two drums. But when looked on the hyperbolic plane, on the Poincaré disks, one can see that actually these domains are isometric. And if they are isometric, then of course that the scattering problem on the hyperbolic plane where it should be considered has the same answer, so has the same poles. So this is the connection to drums. And now I want to end by presenting you a certain riddle and showing another application of our discussion. So we take these two graphs that were constructed by Idan Oren by taking discrete form of the graphs, of weighted graphs, and checking what happens if we replace each discrete weight with a length of an edge, thus turning the graph into metric graphs. Doing so and calculating the spectra of the two graphs revealed that these graphs are isospectral. But we do not know why. We do not know what is the specific construction that can yield these two graphs. So this is one part of the riddle. Then we wanted to check this part of the riddle using our scattering techniques. So what we did was to connect 3 leads to each of the graphs. By the way, one step before, these graphs, though from first sight they might look very similar, I hope that you already noticed, and if not, please notice now, that they are not the same. Okay, the length, there is some variance in the length. Okay, now that having noticed that, let's return the lead and do the following. So we connect leads to each of these graphs, and then we calculate, or actually not we, but Adam Savitsky, which is here in the audience, and this is a very nice plot of poles of the first graph marked with squares, and poles of the scattering matrix of this graph marked with diamonds. And you can see that the poles are in different positions, which means that there is no transplantation, because were there transplantation in this case, we would have that the scattering matrix are conjugate to each other. Or that we did not connect the leads to the correct places, to the correct positions. So at least there is no transplantation between these 3 vertices to these 3 vertices. So in a way, this method of connecting leads is also a technique to check the existence of transplantation. Now the question is what one should do, and then another version is the following. When we plotted the poles of the scattering matrices, we've noticed that we can couple them in pairs. I wonder if you can see that you can match them into pairs, and each pair of square and a diamond have the same real value, or almost the same real value, since it is numeric. So it is a really new finding that we're still not sure what does it mean and if it is at all true, because it seems only numerically. So this is the second part of the riddle. Whether the real parts of the poles are the same, and if so, why? Does it reflect the fact that these original graphs were isospectral? There is only one, as far as I know. Yeah, only one, which is quite close. You can see that it is not exact, but very exact. Still preliminary results that I would happy to discuss. All of us I would happy to discuss. This work was done with my colleague Adam Savitsky, who sits here in the audience, and under the supervision of Uzi Smilansky, my PhD advisor. And I would like to thank you and end with the words of a very smart mouse. Thank you.
We have plenty of time for questions and comments. So, Brian.
To go back to your previous...
This one?
Yeah. I mean, you've chosen one particular way of adding leads on each of the graphs. There are, in fact, 63 ways of attaching leads, and on each of them. So, I mean, you could go through the whole lot.
What, did you say 63?
Yes.
Why specifically 63?
Well, you can either attach or not attach a lead to each vertex. There are 6 vertices.
Right. Actually, there are much more vertices because this is also a vertex in a way. So I can attach leads also to the middle of the edge in a way. So there are actually many more than 63.
Yeah. Well, I mean,
Yeah.
you could get started with the 63 times 63.
Yeah, that's right. That would be very interesting to check. Yeah, I agree. Currently, actually, the only version that we suddenly thought of is that to connect also to these vertices, but then one would get exactly the same graphs. But of course, one can check all the possibilities and see what happens. Yeah.
I mean, another possibility for the isospectrality is that you could look at a few of the eigenfunctions and see whether you can actually guess what the transformation to get from the eigenfunction of the one to the eigenfunction of the other is.
So this is what, in a way, we try to do. This one can do just by taking if I understand you correctly, so Ryan Davis said that one can check the values of the eigenfunction on certain vertices, on these 3 vertices, or on these 6 vertices, and just solve linear sets of equations. And we did it, and there is no linear dependence between either these 3 vertices or the whole 6 vertices between the 2 graphs. So this we did, but have no. So actually, we could have done this instead of attaching the leads. This is an alternative. You're completely right. Yes.
So these graphs are isospectral. Then sort of the determinant of the scattering matrix has to be the same one for both of them. Do they also have the same scattering matrix? Or is there sort of some transformation how to go from the scattering?
Of these graphs, you mean? So the
sort of like, how does the proof of the isospectrality work?
How do we prove the isospectrality? Yeah. One can calculate. So there is actually this goes. Let's go back. Let's go back here.
Yeah. So you sort of compute the determinant of.
So exactly. So we computed the determinant of 1 minus UK for the analytically, and we've seen that again. When I say we, this is Adam Savitsky, my colleague, but we've seen that it is the same. So these are the answers.
So the determinant is the same, or is the matrices related in some nice way too?
The matrix, the UK matrices, you mean?
Yeah.
I do not have an immediate answer for this. Might be.
So as far as I understand, the answer for the real exterior domain is not known yet, only for graphs.
So the answer to what?
Whether the poles of the scattering matrix can be the same for different exterior domains.
So no, the general answer, as far as I know, is not known. We were checking the specific version of the work of Okada et al. That claimed that the poles are different, and then the graphs taught us that if we go back to the original symmetry, then the poles are the same. I am not sure. I would suspect that they are the same because usually people are surprised to find out that the poles are different for isospectral because of the exterior-interior duality, for example. There is a duality between the eigenvalues of the inner problem can be described by the scattering matrix. So I would suspect so, but I really don't know the general answer.
Maybe I can continue.
Yeah,
I have a question now, a remark, because I always somehow try to push the idea that someone has to consider not arbitrary scattering matrices on graphs, but only those which appeared as a limiting processes from three-dimensional domains. And you have a restriction in this case, because you can have a self-adjoint extension of operator on graphs, putting a different type of boundary condition on vertices. And you will have self-adjoint. And in fact, even the choice of vocabulary to use scattering matrices on graphs, but when you just put, when you just use arbitrary conditions on the vertices is very strange. And when you have a three-dimensional domain and it shrinks to a graph, you have a real scattering matrices of three-dimensional domain, and as a limit, you get a specific boundary condition at vertices, not a general boundary condition. And this particular scattering matrix perhaps will have the same pole, will have the same pole for the same.
thanks, Boris. So
Yeah,
that was
sure.
advocate.
Tube around.
Yes, yes.
Okay, it was maybe advocating something which will come later in the program of the workshop. But now back to Harami's talk. Yeah, more questions, John.
Go back to your final slide. Actually, not the one with the joke, not the one with the mouse, the one with the data.
This one?
Yeah. There you go. So is it the case that these, as you say, that they line up, they have the same real part, but they seem to alternate in that the triangle is above the square, and then if you go from left to right, it's triangle above, square above, triangle above, square above. Is that
Yes.
common in the data?
I'm not sure. I don't know.
Fails in the last two actually.
No, the last two are. Actually, the last two.
Hard to see from.
Yeah, it's hard to say, but it seems like maybe they are. These ones come before these ones. Well, it depends how to. I'm not sure.
Okay, Michel.
I'm not quite clear about the story. So you started by showing that these scattering matrices were different numerically. Then you conclude that you have the same scattering matrix. I mean, that's the scheme, but
Yeah,
I mean,
I will emphasize.
Are you choosing different scattering structures?
The question is on what geometry do we work? So Okada et al. Were working on R2, or just on the plane, and they were considering a scattering problem on the plane, and then they got these the results. However, it occurred to us that one should check, maybe one should go to the origin and check the scattering matrix on the hyperbolic plane. And by doing so, suddenly we realized that when looking on the hyperbolic, I was about to think, how will I do it? I don't even know to scatter on the hyperbolic plane, but then I saw that these two domains are isometric, so one don't need even to calculate it.
Using the true symmetry.
Yeah, because this is the true symmetry. So it gives some answer to that work. Yeah.
They were not wrong, they're just not using the right.
They just, it just sheds some light. It's not that I say that they're wrong. Yeah, of course.
Okay, more questions? I see none, so let's thank Rami again.